Hi, welcome back. Hola. How are you? Muy bueno. Nice. All right, we've got our new section. This is 10.5. We're going to talk all about tangents today. Tangents might be familiar for you from when we did trigonometry. This is my 8th period class. Hi, 8th period.
Hi.
Hi. And it's the 6th of March, yes? Cool. Tomorrow's the 7th. All right. Let's kick it off with some definitions. Okay? So our first new word for today is the word tangent. This word might seem familiar to you from trigonometry. When we did the whole some old hippie caught another hippie. Remember that? Yeah. It's the same general idea. We're just going to look at it from a different point of view, and we're not actually using those crazy fractions. So what a tangent is, if you were to draw it, it is a line in the same plane as a circle. So this line and this circle are drawn on like the same bit of wall. Someone graffitied a line and a circle on the same bit of wall. And this line and this circle are running into each other. They're intersecting. And they intersect at one point. Just one. Okay. So let's go ahead and draw our graffiti off here to the side. Okay. So draw a circle. And then you know that on this exact same piece of paper, not the paper of the person next to you, that would be a different plane, on your own paper, you're going to draw a line. It means it goes on for forever. But you have to make sure that it touches your circle in just one spot. I don't care where it touches your circle. Okay? All right, so here's my circle. Okay. And now I'm going to draw my tangent line. I can't draw it like this. Okay? Like if I draw it like that, it's crashing into two places. Okay? It's got to just be one spot. So I'm going to draw it over here, I guess. There's my tangent line. All right, let's start naming these things. Can I have a name for some points, please?
E.
E. Someone else?
J.
K, and I heard J. All right, and I need one more. You've already given me a J. Can I get someone next to you?
Z.
Z, you gave me an E. Get someone else.
L.
L. All right.
Z.
All right. So if I didn't use your letter on this one, it's okay. Hang on to that letter. The Z's, W's. Hang on to that letter so you can help me with some of the other things that we have to name. All right. And this is a lowercase cursive E. All right. So let's write the name of the line that is tangent to our circle. So this line is the one tangent to the circle, and I can name it JK. So note the little symbol for line that I'm writing above the letters JK. So line JK is tangent to circle E. I can also write it in words, line L, and notice I'm using lowercase. Bless you. I'm using lowercase and I'm using cursive for that line. Okay, so line L is tangent to circle E, line JK is tangent to circle E. And those are the same line, they just have two names. I've got one other bit of important information about tangent lines. And we're going to write it right here. Whenever I have a radius, that radius and whatever tangent line it intersects with, the radius and the tangent are going to be perpendicular to each other. What did perpendicular mean?
They intersect.
They do intersect. What angle do they form when they intersect?
90.
At 90 degrees. Good job. That will become important later. Now you notice this special point right here where the circle and the tangent line touch? It's got a special name. That name is the point of tangency. What is the name of the point of tangency in the figure that we drew together? K. Very good. So point K is the point of tangency. Lovely work. That says tangency. I ran out of room. Now it's possible for us to have more than one circle graffitied on our bathroom wall, right? And it's possible for all of those circles to all share the same tangent. And when that happens, it's called a common tangent. So the common tangent is going to be a line or a ray or a segment that is tangent to two or more circles. And let's draw what that looks like. So I want you to draw at least two circles. Now, the trick is if you draw more than two circles, it gets a little harder to find your tangent line. Okay? So draw two circles for sure. And then I want you to find a line that touches both circles in just one spot. And you're going to draw that line. Okay? And I'll draw it with you. Then we'll name a bunch of stuff. Okay? There's one circle. Here's another circle. Sorry. You guys are still writing. Okay, and then I'm going to put my pen here, put my pen here, and that one line appears to be touching each circle in just one location. All right, let's start naming things. So I think I remember on our last naming we had Z. And then someone else had said W. Okay. Q. All right, and one of the ladies. I don't think I've heard from one of the ladies. R. Okay. All right, so what is the name of the common tangent? QR. Good. Now, is the thing that I drew a line, a ray, or a segment?
Oh, the line.
Good. It's a line because I have two arrows. A ray will have one, a segment will have none. So this is line QR, and it is a common tangent. Let's list the circles. Let's see. So far, so good? Nothing too big crazy? All right. Let's introduce our first theorem for this section, and then we'll play around with some figures. And then we'll call it a day, and maybe go take a nap. All right. This is theorem Yes, you. This is theorem 10.11. We'll give it a nickname that we can just use just between the like 16 of us. Okay? And no one else will know. Well, and then everyone on YouTube will be able to call it by this same name. All right. Here's what the theorem says. If two segments from the same exterior point are tangent to a circle, then. I'm going to pause here, and I'm going to draw what this thing might look like. I know I'm going to need two segments, and I know I'm going to need them from some point. Where are these segments going toward? A circle. So I should start off by drawing the circle. So do me a favor, start off by drawing the circle, just anywhere you like. Let's name our circle. Someone who hasn't had a chance yet at all to give a letter. I think you've given one. Hold on to that a bit. I heard W and I heard J, so we'll take both of those. So W there. And then let's grab that. What does exterior mean? Yeah, outside. So somewhere outside of the circle, there's this point which we'll use, his letter will use J. So somewhere not inside of the circle, somewhere outside the circle. I'm going to put it there, and I'm going to name it J. I need two segments that come from this exterior point, J, and go toward the circle and are tangent. What does that mean? What did tangent mean again?
A line in the same place as the circle that intersects the circle at exactly one point.
It intersects the circle at exactly one point. So I'm going to go from J toward the circle, and I only want to hit the circle once with this line. Okay? All right, so I'm going to turn my paper just so that way it's easier for me to draw. Okay, that looks like it's touching the circle in just one spot. There it is. And I'm going to do that with the other segment. I don't want to go this way. Yes, it looks like I'm only crashing it into one spot, but if I were to continue the line, it crashes in two. Okay? I only want it to crash in one spot. So I'm kind of being very picky about where my line is. All right, so I've got something that looks like this. Can I please have two other points from someone we haven't heard from yet at all? Can I have a point name? Just a letter. Your favorite letter. S? Okay. He totally borrowed your letter. So since he borrowed your letter, can you give me another one? A. All right. So there we go. Let's finish our theorem, because now we have two segments that come from the same exterior point, and they are tangent to a circle. When this setup happens, they are congruent. Wait. What they? The 2 points? But I have like a lot of points there.
A and F.
These 2 points? Okay, what does congruent mean? Same size, same shape. Do points have size? They don't. So I can't consider points being congruent because they don't have any size to talk about. Okay? So something else has to be congruent when I have this set up. But I only have one circle. And they means more than one. So what other kinds of things do I have on this figure that I have more than one of? I have those line segments. So this word they is referring to the 2 tangent segments. This segment and this segment. are congruent. What does this thing kind of look like to you?
Triangle.
Okay, a triangle, but it's got a circle on its end.
Cone.
Like a cone. Like a raspa, right? So let's nickname this theorem something like the Raspa theorem? Okay. All right. So we'll call this the Raspa theorem, and we know that that's a snow cone? All right. So we're going to call this is our little pet nickname. This is the Raspa cone theorem. So this way you can talk about this and no one else except everyone who watches this video will know what you're talking about. Thumbs up for raspas in the summer. Oh yeah. I had a couple nuts. All right. Let's do some examples and let's play with this. I've got just enough room on the bottom of my page for these examples. If you don't feel you're going to have enough because we got to do some drawing and some algebra, you're welcome to turn to the back of your page to run your examples or a fresh sheet of paper. All right, the directions for these examples, we'll do at least two. Say, find the value of x and assume tangents. Basically what we mean by assume tangents is if it looks like it's tangent to the circle, it is tangent to the circle. We're not going to try to freak out. Bless you. All right, here's my first figure. I need you for number 1 to draw a circle. Name it A. Draw some points exterior to the circle. Name it C. Take your straight edge and you're going to draw 2 tangent segments from C toward the circle. So start at C, go toward the circle, and make sure they're tangent. Only touch the circle in one spot. We're going to label this segment x plus 3 and this segment 7. All right, looking at number 1. We've drawn it beautifully. Do we have the setup for our Raspa theorem? Yeah, we got a circle. We got some points sitting outside the circle, and we got 2 segments tangent to the circle. They're coming from that same point. We have the setup from the Raspa cone theorem. So when we have this setup, that's what the if says. Then what can we say? They are congruent. They what? Which they? The 2 tangent segments are congruent. So this thing is congruent to this thing. Congruent means same size, same shape. And so that means that BC and CD have the same measure. So this measurement is the same as this measurement. And now I have a real simple equation that I can solve for x. How do I get x by itself? Subtract 3 from both sides. And when I've subtracted 3 from both sides, x equals? Beautiful. Did I find what I was looking for? Yes, because the direction said find the value of x. I'm done. Easy enough, huh? Let's work on number 2. Here's what number 2 looks like. Draw a circle. The best circle you have. It doesn't have to be perfect. Name it H. Give me a point somewhere on the circle and name it J. Then give me some point outside the circle and name it K. Connect the 3 points. You have a beautiful little figure. Put it away. All right, what kind of segments do we have here? What kind of line segment is this, J to H?
Radius.
It's a radius. And what kind of segment is this, J to K?
Tangent.
A tangent. And when we have a radius and a tangent, how do they intersect?
Perpendicular.
Perpendicular. I have a 90-degree angle right here. Good. Our radius is 15. Our tangent segment is 20. And we've been told that the segment connecting the center of the circle to that exterior point is some measurement x. What kind of shape did we just create right here? What kind of triangle? What kind of triangle?
Trapezoid triangle.
We don't have anything called a trapezoid triangle.
Right triangle.
Right triangle, because we got a right angle. That's okay. You were testing me, weren't you? Yes. I have a right triangle. And when I have a right triangle, what kinds of things can I do to find the measurements of right triangles? What can I use? Yeah, the Pythagorean theorem. A squared plus B squared equals C squared. You guys are so sick of doing this one, aren't you?
Yep.
And you're going, dear God, where's the shortcut, right? Let's check. Our shortcuts are Pythagorean triples, special right triangles, or trigonometry. For trigonometry, we have to know something about those acute angles, the ones that aren't the 90. Do we know anything about those angles? No, so we can't use trigonometry. Let's check to see if this is a special right triangle. We have two kinds. We have the 45, 45, 90 and the 30, 60, 90. For the 30, 60, 90, we have to know that the angles measure 30 and 60 and 90. And do we know anything about the angles? No, so we can't use that one. Is this a 45, 45, 90?
Yes.
We'd have to know something about the angles, which we don't. But we can look at the legs. If the legs are congruent, it's still 45, 45, 90. Are the legs congruent? No. So we can't use special right triangles. And so the only other shortcut that we have left is to see if this thing is a Pythagorean triple. Here are the two main triples that I highly recommend that you memorize. Because in all of those college entrance exams that you're going to have to take, a lot of the questions dealing with right triangles use these. Okay, so if you have these memorized, those things that go from, oh my God, this is too complicated, turn into, poof, I know this. Okay? So what I'm going to do is I'm going to play a little number game with myself. I'm going to start with this bottom one. I'm going to ask myself, what do I need to multiply to 5 to get to 13? What do I need to multiply to 5 to get to 13? 15.
3.
Yeah, 15. 3. So 5 times 3 is 15. If I multiply 12 by 3, do I get 20?
No.
No. So it's not this Pythagorean triple. I'm going to check this other one. And if this other one doesn't work, then I can't use Pythagorean triples, and I have to actually use this formula, and I have to solve it the long way. Dear God, please let this one work. I don't want to do this mess. Okay.
Hello?
Yes?
Ma'am, do you have Salvador Garcia?
I do.
If we can have him come to the office for just a moment.
Okay, can it
Thank
wait
you.
till we're done?
I'm sorry?
Can it wait for a few minutes?
Okay, yes.
Thank you. All right, when we're done with this exam. All right, so now I'm going to play that number game again, but this time using my other triple. 3 times what is 15?
5.
5. 4 times 5 is
5. Or 20.
20, and that's what I have here? This is 20?
Yes.
That means that I can take this 5 and multiply it by the 5 I was multiplying the other things by to get my answer. Let's review the triple again, because this looks like it was magic, okay? What I did was I took this first number right here, and I figured out what I need to multiply to it to give me this smallest number here. 3 times 5 is 15. I took that 5 and I multiplied the next biggest number by it, and I checked to see, do I get the next biggest side measure? Yes. Because it's a yes, I can immediately take the largest number, multiply it by 5, and it will give me the hypotenuse. I did not have to use the Pythagorean theorem because it was already done for me. Ask your question. I see the thinking face.
How did you get to 25?
How did I get the 25? Since I did 3 times 5 and 4 times 5, I did 5 times 5. And that's a magic trick you can play every single time. And if it works, then you just write the answer and you're done. You don't need to go through and do this. Okay? Sounds good? All right. I've got another example. Do you guys want to do it, or do you want to scoot on to the next topic? We've got like 20 minutes. Scoot on to the next topic? Right on. Let's scoot on to the next topic. I need an issue of paper. You guys are awesome. All right, this is 10.5 continued. We're still looking at tangents. Just take the whole stack of paper. Just bring it right down with you. Nicely done. And whatever paper you don't use, you can put back later. Thank you. We talked about circumscribed. You remember that word, circumscribed? What did circumscribed mean? Do you remember what circumscribed means? You can say no. No. Okay. It means to draw it around something.
Mama,
Yes?
do you have Robert Villa Gomez?
No.
Is he absent or you don't have him?
He's not. He's absent.
Okay, thank you.
So a polygon is circumscribed. It's drawn around the circle. If every side I did mean about. It means the same thing in this context. When you circumscribe something about, you're drawing it around. Okay. Thank you for making me stop and answer that question. It ends up drawn around the circle if we can say that every single side of the polygon is tangent to the circle. So if I start with a circle and I make sure that when I draw my polygon, all of those sides only touch the circle in one spot, we're in good shape. Okay? So let's draw a circle. Go ahead and name it. So you can go whenever you're ready. H. Okay. All right, now let's draw a polygon circumscribed about this circle. Okay? Which means I need a bunch of tangent lines. So I'm just going to start drawing tangent lines. Okay, there's a tangent line. I need to get this to be tangent here. No, because they called you. Thank you. There we go. I'm going to try another one here. There we go. Can I get this last side to be tangent? Yes, I did it. It doesn't matter how many sides your polygon has. I managed to get 4. If you can only get 3, that's fine. If you're extra and can get like 6 sides tangent, you're amazing. But notice how we have every single side of this polygon only touching that circle in one spot. I'm gonna draw a non-example, just so that you can see what it looks like when it's not tangent, okay? Okay, you see how the one on the left, or excuse me, the one on the right, one of the sides of my polygon goes like through the circle? Yeah, it's not circumscribed, okay? Now this whole circumscribed business thing makes stuff really awesome. Because check this out, look right here. If I were to cover most of this up, if I were to look just right here, what does this thing look like? Just right here, what does it look like right here? Kind of a triangle, but I've got like this round thing, yes? Yeah, it looks like the bottom part of our cone, like our Raspa theorem, doesn't it? That looks a lot like this. I need another little piece of paper. I can do that. Don't these two things kind of look the same? Which means I can use my Raspa theorem again here because this piece and this piece are congruent to each other. What about at this other corner? Same thing. I'm using two lines because they may not be the same size as the first set, right? It might be a different size Raspa. Like this one's a medium and this one's like a large, right? What about right here?
Yes, but it's small.
Yeah, but it's like really tiny, right? That's okay. Like it's super tiny. I can't even get in the number of bars in there. What about right here?
Yes.
Yeah, again, but even tinier, right? If I had drawn this bigger, it would have been better. All right, let's do one example. One more example from this, and then we'll call it a day. We'll be done, I promise. All right, let's draw. Let's look at number 12. So when I provide you the printouts, you'll have number 12 done. Okay, so I'm going to circumscribe a quadrilateral around my circle. You all right? Okay, so I went a little crazy on the corners, but just pretend these aren't there, okay? All right, I'm told this piece right here is 5, and this piece over here is 9, and this piece is 4, and this piece is x plus 2, and this piece is 8. And our directions say, find the value of x, then find the perimeter of the polygon. And that's the only information we've been given. All right, what's going on right here in this corner? What's going on in this corner right here? Does this look like a Raspa theorem up here in the corner?
Yeah.
Yes. So since it looks like a Raspa theorem, this segment and this segment are congruent, which means I can write my equation like this. What's the value of x? Subtract 2, which is 6. So I've done the first thing. I found x. Now I need to find the perimeter of the polygon. I know now that this part, I'm going to write in a different color so we can see it. This is 8 because this was 8. Down here, right here in this corner. I know this piece is 4. So how much is this piece? Also 4. Good. And now I'm looking at this corner. If this piece is 9, then this piece is? Good. Now I'm looking at this corner. If this piece is 5, then this piece is? Perimeter means the distance all the way around. So I'm going to add up all of these little pieces to give me my final perimeter. That's a lot of numbers. Maybe someone has a calculator. You know what? I can do doubles. I know my doubles. 26 plus 18 plus 8. 36? I think it's a little bigger. Oh, you're still thinking in your head. I'm sorry. 52? Oh, because this is 26 also, right? Okay. And there's our perimeter. Phew! We did it. Good job moving on to the next section today, guys. I appreciate it. Thank you very much.